Hello everybody, my name is Saeed Hashemi. Today I'm going to give you a short presentation about shear strength of soils, which is one of the most important basics of geotechnical engineering. Here is the outline of my today's presentation. First, I'm going to introduce the shear strength of soils and define the shear failure concept. Then I'll explain the Moore Coulomb failure criterion, and finally I'll explain the shear parameters related to these criterion. Okay, what is the shear strength of the soil? Shear strength is defined as the internal resistance per unit area that the soil mass can offer to resist failure and sliding along any plane inside it. In fact, various studies showed that soils generally fail in shear under different combination of stresses. As you can see in this figure, if at a point on any plane within a soil mass which is under loading, such as this embankment or this strip footing, the shear stress becomes equal to the shear strength of the soil, then failure will occur at that point. Therefore, we need this knowledge to analyze the stability of soil masses. So, in case of constructing any structure, such as a building or a bridge, the safety of that structure closely depends on the shear strength of the soil. As you can see in this photo, underfooting soil failed in this grain elevator in Canada, and then the structure collapsed while it had no problem in its building elements such as beams or columns. We know that soil is a material comprised of discrete mineral grains and decayed organic matter along with intergranular gases and liquids. As shown here, when the shear stress along this surface reaches the shear strength of the soil, failure happens. In case of a shear failure, the soil grains, which is here, slide over each other along the failure surface, and crushing of grains won't occur if the soil is not consolidated. Actually, these two photos are examples of shear failure due to landslide phenomenon. Originally, the shear strength of a soil at a point on a particular plane was expressed by Coulomb as a linear function of the normal stress at failure on the plane at the same point. In this function, as you can see here, tau f is the maximum shear stress the soil can take without failure under normal stress sigma. Thus, failure will occur at any point in the soil where the critical combination of shear and normal stresses develops. Also, as you can see in this graph, the state of stress in two dimensions can be shown on a plot of shear stress versus normal stress sigma. In this graph, derived C is the cohesion of the soil, and phi here, which is this angle, will be the angle of internal friction or friction angle. Actually, a friction angle can be defined as the angle of repose which the soil settles naturally. So a firm soil will have a steeper angle of repose than a loose one. As I mentioned before, shear strength has two components, cohesive and frictional. In this slide, you can see the different values of cohesion and friction angle for different soil types. For example, in case of pure gravel, there is no cohesion between the grains, and C is 0, and the shearing resistance is developed only by interparticle forces by phi. Or in case of plastic clay, which is shown here, the only parameter that resists against the shear is cohesion, and phi is 0 because there is no friction between the grains. It should be noted that the relationship between tau and sigma can be nonlinear for some soil types. And finally, you should note that the higher the values C and phi, higher the shear strength of a soil. Okay, more circles. Any stress state can be represented by Coulomb equation, as I mentioned before, and also a Mohr circle, which is here or here, can be defined by the total or effective principal stresses sigma 1 dash and sigma 3 dash. We can draw the Mohr circles for different test conditions. For example, if the combination of stresses touches the failure envelope, the element will fail, as shown here for element X. But in case of element Y, the Mohr circle, as you can see here, will not touch the envelope and element remains safe. In this element, element Y, with applying the delta sigma stress after the hydrostatic stress condition, Mohr circle becomes larger. And with this stress condition that we have in here, the soil element does not fail. Why? Because the Mohr circle is located within the failure envelope. But please note that Mohr circles cannot extend to the area above the envelope, because when it touches the envelope here, this is the failure envelope, the element fails and it is not possible to pass this line. In this slide, you can see that with increasing the delta sigma or deviatoric stress, Mohr circle becomes larger until touches the failure envelope, and the sample fails at exactly this point. It should be mentioned that the shear stress in a soil element can be resisted only by the skeleton of the soil grains. So we need to consider the effective stresses if we have underground pore pressure. So in this case, we have to calculate the effective stresses and then we can draw the Mohr circle, as you can see in here, instead of the Mohr circle that we can have with the total stresses. And also the center of the Mohr circle and also the maximum shear stress can be calculated by these two simple equations. If we have these sigma v and sigma h according to our experimental test, then we can derive the sigma dash, sigma v dash and sigma h dash, and then we can draw our Mohr circle easily. For finding the failure envelope by Mohr circles, we need to test several identical specimens. In the first stage, we need to apply the hydrostatic stress condition to the specimen, and in the second stage, we will increase the deviatoric stress or vertical stress to the specimens until the specimen failed. So with each test, we will have one Mohr circle. So we need at least 3 Mohr circles to be able to draw our failure envelope. And in case of total stress and in case of having underground pore pressure, then we have to calculate the effective stresses from the total stresses, and then we can draw our Mohr circles in terms of sigma dash, and then we can draw our failure envelope easily. But keep in mind that with increasing the number of tests, we can have more precise failure envelope. And finally, the last slide is about the orientation of failure plane. As you can see here, the orientation of failure plane in a soil element which fail due to the combination of shear stress and normal stress as well can be calculated as a function of friction angle. It's equal to 45 degrees plus 5/2. Actually, this angle theta can be also shown on Mohr circle, which is 2 times theta, and the stresses at failure point tau f and sigma f dash can be calculated as a function of effective principal stresses sigma 1 dash and sigma 3 dash. So we can calculate these 2 stresses based on the applied stresses that we had recorded in the experimental test in the laboratory. I hope you enjoyed the presentation and thank you so much for your attention.